Hello, period 7. Sorry I can't be there today. I'm trying to get healthy as best I can. We're starting formally section 9.1. This is Introduction to Sequences. So, yesterday I asked you to download chapter 9. Hopefully you did. If you didn't, you got to play some catch up and get that thing downloaded. Alright, with sequences today we're going to look at introduction. There are two types of sequences. There are recursive sequences, and there are what are called explicit. And I'll explain more about this as we go through. We're going to focus first on recursive, and let's review the Fibonacci sequence. Okay, maybe one of the biggest things we have to learn in this particular chapter is the notation. All right, we need to make sure that we understand the difference in the notation between n and what is meant by a sub n. So I'm going to set up a table here of the Fibonacci sequence. Now what n represents is the number in the sequence in terms of the first, second, third, fourth, fifth, sixth, etc., or up until the nth term in the sequence. In the Fibonacci sequence, we go 0, 1, 1, 2, 3, 5, etc. Okay? So, if we were to say, for example, okay, what's the fifth number in that sequence? So, if n equals 5, that means we're dealing with the term that's in the fifth position. Okay? So, in that particular circumstance, we're looking here. Okay? So, if n is 5, a sub n, which in this case would be, get a little eraser going. In this case, we'd be talking about a sub 5. Need a pen tool. There we go. A sub 5, right there, a sub 5 is 3. Okay? A sub 6, by the way, is 5. Okay? So that's some of the notation. Now, as we deal with the Fibonacci sequence here, we are going to see if I can get a blank page. Whoops. How to do that. Okay. All right, so dealing more with this Fibonacci sequence, then it is recursive. So now we're going to write the rule. Okay, now what's meant by recursive, my stylus is awful, by the way, that's why I can't print nice and neat. I look like I'm printing like a kindergartner. Anyway, a recursive is the next term is based upon the term before it in the sequence. So the Fibonacci sequence is the sum of the two previous numbers, right? 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc. There's a little hint as to why I'm not there. All right, now, so the rule to get the nth term in the Fibonacci sequence, it's the sum of the two preceding terms. So we would take the term 2 spots below, which symbolically is a sub n minus 2, plus a sub n minus 1. So therefore, if we were going to get the sixth term in the Fibonacci sequence, it would be a sub 4 plus a sub 5. Or the sixth term would be equal to the fourth term, which is 2, plus the fifth term, which is a 3, gives us a sub 6, which is 5. So this is an example of a recursive rule, a way to define the next term based on the terms preceding it. So as an example of a recursive rule, let's say we were given a sub 1, meaning the first term in the sequence is -5. And the rule says a sub n is equal to a sub n minus 1 minus 8. And our goal is to write out the first 5 terms in the sequence. Okay, so n and a sub n, we have to write out the first 5. So the first, the second, the third, the fourth, and the fifth. It's given that a sub 1 is -5. Now a sub n, according to the rule, is the previous term. So a sub 2 would be the previous term, a sub n minus 1, minus 8. So that means that would be -5, the previous term, minus 8, or -13. A sub 3 is going to be a sub 2, the previous term, minus 8. So if we subtract 8, subtract 8, subtract 8, we have the first 5 terms of that recursive sequence. Another example, say a sub 1 is equal to 2, and a sub n, here's the rule, is equal to -3 times the a sub n minus 1, or the previous term. Again, our goal is to write out the first 5 terms. So n and a sub n, the first, second, third, fourth, and fifth terms in the sequence. It's given a sub 1 is 2. So now the second term is equal to the first term. No, it isn't. According to the rule here, a sub 2 is equal to -3 times a sub 1. So we take the previous term and multiply it by -3. It becomes -6. A sub 3 is equal to -3 times the previous term, or now +18. The fourth term would be whatever we would get if we multiplied 18 by -3. I think that's -54 if I do it in my head. And then if you multiply that by 3, we get what? +162. Okay, those are guesses right there. Mental math hopes. Okay, so those are examples of recursive. Now we're going to get into the second type, and those are going to be explicit. If I could spell, again, printing like a kindergartner. So let's give us another sequence. Okay, let's do n and a sub n. Let's create a sequence here. The first, second, third, fourth, fifth, ... out to the nth term is 1, 4, 9, 16, 25. So what I'm making here are the list of perfect squares. Now, since this is an explicit sequence, what it means is I can define what the sixth term is going to be without needing to know what the fifth term was. Okay, so a sub 6, we can find this without knowing previous ones. Okay, because a sub 6 would simply be 6 squared, or 36. I could skip ahead and find a sub 10, and I do not need to know the ninth term to do it. A sub 10 would be 10 squared, or 100. So what that means is we can write a rule for this, that a sub n is equal to the location in the sequence squared. That's that explicit rule there. So look at a couple more examples. Okay, one thing you're going to be asked to do is if given an explicit rule, like say a sub n is equal to n squared minus 2n, find the first 5 terms. Okay, so this is an explicit rule. Notice here, there's no a sub n minus 1 stuff going on here. We don't need to know those previous terms. Okay, so n and a sub n. N is going to be the first term, second term, third term, fourth term, and fifth term. Got to find the first 5. So a sub 1 would be 1 squared minus 2 times 1, which I believe is negative 1. The second term would be 2 squared minus 2 times 2, which is 0. The third term, right here, would be 3 squared minus 2 times 3, which is 3. The fourth term would be 4 squared minus 2 times 4, which is 8. And then this last term would be 5 squared minus 2 times 5, or 15. So now we've used this explicit rule to write out the first 5 terms of that sequence. What I think is going to be the hardest thing for you guys to do is going to be to write explicit rules. So say we've got this sequence, 7, 5, 3, 1, negative 1. So the rule, okay, clearly what's happening is we're subtracting 2 each time. So a recursive rule is easy, right? The next term is found by taking the previous term and subtracting 2. But now to get the explicit rule, which is better, explicit rules are better, okay, here, since we're constantly decreasing by 2, it's linear. So we start at 7, and we're decreasing by 2, okay, so that would be the explicit rule, because if you look, n and a sub n, 1, 2, 3, 4, 7, 5, 3, 1. So to go from here to here, this is the second term, but you subtract 2 once. So it's the second term, right? But you start at 7 and you subtract 2 one time, one less than its location. So again, I think writing these explicit rules is harder. So maybe that made sense, maybe it didn't. We will see. Okay. Another example would be, say you have 1, 1/2, 1/3, 1/4, 1/5, etc. Okay, so now the nth term is a fraction, and it happens to be 1 over n. Okay, because the first term is 1 over 1, the second term is 1 over 2, the third term is 1 over 3. So that explicit rule is probably easier than the first one. Anyway, good luck. Try the homework. It's up on the homework page. You can check it out. Hopefully I'll be back tomorrow to answer any questions.